Hey guys, so today for this third concept video, we're going to actually be talking about something that most people can recognize as more mathy or physicsy and soulless, and we're going to be talking about real live equations. Yeah, that's right, real live equations, real mathematics, and it's not just going to be me rambling on and on. So this time we're going to try looking at how can we find magnetic force. And we're going to take things that we know about these systems of wires or moving charged particles, and we're going to see how we can transform what we know into what kind of magnetic force we would expect to see. So to do that, why don't we look at what we do know about our two systems, namely the wire and the charged particle. Alright, so when Ampere was making his observations with the wire, he noticed that two main things affected how much force that wire felt. And namely, they were the length of that wire and how much current was running through that wire. And length is a vector that is defined as going in the direction of current, and current is simply a scalar. Alright, and now for this moving charged particle, last video, we saw that magnetic force, is a relativistic phenomena. And with all relativistic phenomena, as the speed of our reference frame increases, we are going to notice more of these relativistic effects. So as velocity increases, velocity because it's a vector quantity, we are also going to notice more magnetic force. And now we need to think about what else this magnetic force is going to be related to. And we saw that magnetic force is actually a relativistic distortion of electrostatic force. And as a result, what would normally affect the electrostatic force on this particle will also affect the magnetic force on this particle as it begins moving with velocity. And as a result, we can deduce that charge must also play a factor here. Yet, these are not the only things that seem to be affecting magnetic force. For instance, if we move these two wires further apart, Ampere noted that they felt less of an attraction or less of a repulsion between each other. And for these charges, if we move two charges further apart, that you would notice less of a magnetic interaction between them, because the electrostatic force that you perceived as distorted in order to get the magnetic force is actually not as strong in the first place there. Which means that there's going to be external factors that we are just going to, for now, sum up into this idea of a magnetic field B. And we've seen this concept of a magnetic field, or we've seen this concept of a field more generally before. For instance, when we ran into electrostatic forces in other branches of physics, we started to learn that charge is the main thing driving electrostatic force, the charge of a particle, yet it also depends on external factors that we later nailed down into Coulomb's law, but we just generally summarized as electric fields. We also noted the same thing for gravity, where gravitational force, weight, doesn't just depend on mass alone. So yes, I am massive, or I do have so much mass, and that does mean that I have weight because a gravitational field is interacting with me. Just like a charge has so much charge, and that doesn't mean it has electrostatic force, but that electrostatic force also depends on the electric field that's messing around with that charge. But it's important to note that there is actually a big divide between these two different concepts of field. And that concept is that electrostatic force and gravitational force respectively depend on charge and mass. So if this depends on charge and this depends on mass, that means that they depend on scalar quantities. I can just say however much mass I have. I'm not going to do that because I don't want to say how massive I am, but I can say how much mass I have, and then as a result, I could figure out how much force I have, no problem. I don't need an extra direction, and it wouldn't mean anything if I specified a direction. I couldn't just say that I have that much mass north, east, south, or west. It would all just be the same. I would just all have that same amount of mass. Just like you can't say an electron has negative charge up or negative charge down. It just has negative charge. And as a result, that's going to be a little bit different, because if you notice back here, towards these dynamic duos that we know are responsible for magnetic force, you'll notice that magnetic force is inherently tied to this idea of motion. It's inherently tied to this idea of moving charge, whether it be down the length of a wire or whether it be through space in a particle. It's inherently tied to this idea of motion. And as a result, we're going to have to figure out some way to get this vector quantity, these vector quantities, and this magnetic field vector quantity into a third vector of magnetic force. And the way in which we do that ends up becoming the cross product. So let me start explaining the cross product. Let's just start with a little bit more conceptual mathematical idea of the cross product. So the cross product is going to be one of the ways in which we multiply vectors. And the cross product is unique from the dot product, the other way to multiply vectors, in that it adds up perpendicular components. It adds up perpendicular components, it multiplies those perpendicular components, and then it spits out a vector. Another difference from the dot product, which spits out a scalar. So for the cross product, what you end up doing with these two vectors, let's just call them A and B for now, is you will split one of these up. Let's just split up the slanted one into a component along the other one, so the component of A along B, and the component of A that cannot be assigned to a direction along B. This other, and then we simply multiply this component and B. In doing so, will actually yield you the area of this parallelogram, which is why the cross product, or the magnitude of the cross product, is sometimes referred to as the area of a parallelogram, which is also then yields this formula that A cross B, the magnitude of A cross B, will equal AB sine theta. Yet it's very important to note that the people who write questions on physics exams are evil. And the reason they're evil is they realize that some people like to just memorize these formulas, and then when they take these formulas and apply them, just taking whatever theta they're provided in the problem, they don't realize, I don't realize, that this theta is actually not the one that's being referred to in this situation where this formula came from, but this theta might be some other theta. And as a result, that the magnitude of the cross product might actually be AB cosine theta, depending on whatever the heck the problem wants to call theta. So in other words, make sure to always be careful. This is a good formula to use on the fly, but if you really want to be precise, if your life depended on it, I would just go back and find the area of the parallelogram, because this makes sure that you never screw up. This makes sure that you always find the perpendicular component, and that's how you find the magnitude of the cross product. But now, we've also said that the cross product spits out a vector, and that force is a vector. So what direction is that vector going to be? We just found the magnitude. Well, what's the direction of this force vector going to be? In order to find the direction of this force vector, let's actually draw that parallelogram back up. And this parallelogram defines a plane. The same parallelogram that we used to find the area defines a plane, and since we know that the cross product is perpendicular to both of these original vectors, A and B, then it's actually going to also be perpendicular to this parallelogram and the plane defined by it. And that gets our direction down from an infinite number of directions down to a 50-50. And if you have to choose, and the way you get down from that 50-50 to one answer is a coin flip. All right, so the way that you reliably get from a 50-50 to the right answer is actually called the right-hand rule. It's a little bit more complicated than a coin flip, but if you have to use a coin flip, I mean, why not? It's going to be, and let's say we're going to try and find the direction of A cross B, which is, as you will see, distinct from B cross A. And we're going to see that in just a second. Now, the version of the right-hand rule that I immediately default to for some reason is that I take my right hand out and I sweep it from A to B across the smallest angle theta that I can. So I don't do anything like this. I just simply take it from A to B and sweep it. If I have to turn my wrist more than half the way, I know I'm doing it wrong. I would also end up picking, like, let's say 130 over 230. And A cross B lets me know that this vector is going into the page, which I denote with a cross. That I'll just show you here real quick. But notice that if I did B cross A, that I would be sweeping my hand from B to A across that angle, and that would actually get me a vector that's out of the page. So A cross B is not equal to B cross A, but it is in fact equal to negative B cross A. So that is how we find the direction of the magnetic force, or the direction of any cross product for that matter, if you wanted to find torque. But now, let's get out of math world and let's start taking what we know in order to find magnetic force more broadly. And now we get that magnetic force will be equal to Q V cross B, and that magnetic force for a wire will equal I L cross B. So here you have the first dynamic duo for the charged particle, and here you have the second dynamic duo for the length of wire with current running down it. And again, one more time, this length is defined as the direction in which current is running. So if this is my dynamic duo vector for here, which is wire wrapped in electrical tape, you'll notice that current will be running from this tail end of the vector, the cross, up to the dot. And that's how we define the direction of the length. Anyways, guys, this is how we find magnetic force. If there are any questions, I know this is a little bit more of an abstract video, please feel free to leave them down in the comments and leave any of your suggestions. I really would appreciate some feedback, likes, subscriptions, whatever you want to do. And thanks for at least watching and hanging on in there. I'll see you next time, where we'll explore some of the more or stranger properties of this new unique force. See ya.